I like to start out with why is it important to look towards green chemistry and sustainability. And um, a lot of people, especially very young folks like yourself, don't remember or don't know what it was like before EPA started regulating pollution in 1970. Before EPA, there were some agencies that worked on some stuff. They mostly helped by relying on this idiom, dilution is the solution to pollution. So they would just make stack heights higher and they'd send the problem somewhere else. Which was interesting when you had stacks at different heights and you had one stack of air emissions going this way and one stack of emissions going another way because of different layers of air. And it just goes to show you that, there isn't a way, and you're not curing it, you're sending it somewhere else, because there is no way. It just takes longer to build up, or weather patterns to be bad, to make it problematic. Similarly, when you had, or an example of that is in Denora, Pennsylvania, where they were in a valley and they had coal burning industry, and they had an inversion one day that trapped all this stuff in the town. It killed 70 people. It made about half the population sick, and it killed a whole bunch of cows. So it was quite made quite an impression on people. There was a book written on it called "When the Smoke Ran Like Water." Similarly, the Cuyahoga River got stuff dumped into it because, hey, we'll just throw it in the river and it'll go somewhere else and it'll mix in. Um, and a lot of it didn't mix in, as y'all know as chemists. A lot of it would float on the surface, and sometimes that could catch on fire. And after that happened a few times, people started to think maybe that doesn't work so well. DDT is a really good example of something that they thought it was going to be a magic bullet. They thought it was, this miracle that would cure diseases like malaria, and they ended up just using it willy-nilly, all over the world, and it had severe consequences. It was something that would magnify up the food chain. It magnified up it to especially top predators of fish, and birds like pelicans and bald eagles were nearly extinguished. I grew up in South Florida, and there were no pelicans there that you could see when I was growing up, and now they're just everywhere. Uh, the other thing that Rachel Carson pointed out was that it was also producing fertility and neurological problems in humans. So we are also top fish predators, and that wasn't a good thing. So people sometimes think this is all in the past, but in countries where they don't have good controls for pollution, they have still the same kinds of problems. They still, do it the easy way, the way that the Americans started it. And this is Beijing just a couple of years ago, pre-COVID. So those are air pollution masks and not COVID masks. So EPA did start putting controls on things, but they really tended to be, let's put something on the end of the pipe, and we create these filters that would create these other problems. They would create these, okay, we've got these baghouse filters full of, stuff from coal plants, and we've got these effluent filters with contaminated water. What do we do with that stuff? And so we do have some regulations that encourage pollution prevention type techniques, but they aren't usually used. They're not the easiest thing to do. They have to be on a one-by-one basis, and it isn't the first thing people think of, because people like to say, well, I've always done this way, and if you tell me I have to add something on, fine, I'll add something on. I'll complain about it a lot, but I'll do it. But the problem is that people, in order to do a pollution prevention approach, you have to rethink the system. Another problem is the whole issue of ecological footprint. So if you think about the resources that it takes to create your lifestyle, to create the food that you eat and the roof over your head and the car that you drive and the clothes that you wear, if you think about that in terms of how much of the earth does it take to provide all that, that is your ecological footprint. Now, the US is 5% of the global population, but we use 25% of the resources, and we emit 25% of the greenhouse gases. So that's like 5 times our fair share. Here, I've shown you my footprint compared to the US average. Now, I live a pretty green life. I drive a Prius, I walk or bike most places that I can. I used to van pool to work, and I don't eat a lot of meat. I did travel a lot for work. I don't drive my car much. I don't throw a lot of things away, so I don't have a real high goods and services footprint, which is measured by waste. And so you can see my footprint compared to the country average is way down. I do pretty damn good for an American. But I would still, if everybody lived like me, it would still take almost 3 Earths. And part of that is just because we have created this system in which the things that we do, the things that we eat, the things that all these patterns that we have added up to a very wasteful kind of a lifestyle. And yet there are Americans who are complaining because, you know, people in India want refrigerators. So obviously we can't keep that up. We've only got the one. I was doing the ecological footprint, the little quiz with a group of high school science kids once, and we were doing it in the computer room, and they were playing with it like it was a video game, and one kid got it up to 25 planets, and one kid got it down to 1. And then this kid in the back of the room waves his hand and he goes, "How many do we get?" So if you talk about sustainability, everybody you ask kind of is going to have a different definition. And I got tired of people saying, well, we have to define sustainability before we can actually figure out what we need to do, which is, you know, denial by delay. So I went and started searching Google, took the top 35 definitions that I found and did a word cloud of them. And this is what you get. And this gives you a really good gestalt of what sustainability is about. It's about the environment, and it's about the needs that people have in the future and you know, future generations. It's very much about intergenerational equity. It's about consumption and energy, and there are social aspects and there are economic aspects, and there is, you know, nature that's very important for us. So this gives you a good idea, even if it's not this is a definition, because you don't really need to know the definition per se. But you'll often hear it described as this 3-legged stool where you want to, quote, balance the 3 legs, economy, environment, and social equity. But in fact, if you think about function and the functions of the systems, the economy cannot exist or function without a stable society around it. And a society cannot exist or continue if it doesn't have an environment that provides what we need. Top priority, clean air to breathe. Second top priority, clean water. Third top priority, you know, food. After that, everything else comes lower. And those things are very dependent on a functioning environment. So one of the reasons for that is, ta-da, ecosystem services. And these are all these services that nature provides for us, from the you know, multitudes of organisms that live in the soil system and create soil fertility and break down things to make more soil that makes the food that we eat, to the aquatic system where we have the water cycle, that, you know, every bit of water that's on the earth is the same bit of water that has always been on the earth, and we are no doubt drinking dinosaur pee from many, many, many eons ago. We have really complex systems like aquatic ecosystems, and we have things like, you know, terrestrial systems where we have the things that we are so used to thinking about and that tend to be the sort of charismatic macrofauna that people are fond of when they talk about nature. But nature is so much more than this. I love this. I love this diagram. And John Muir once said, when we try to pick anything out by itself, we find it hitched to everything else in the universe. And so this is a picture of the simplified food web of the Atlantic cod. And what you see is everything is really connected. And it goes up into the air to the fish, to the birds that eat the fish. And cod, of course, is a huge food source for human beings. You know, people who eat fish and chips and fish sticks, all those used to be all cod. And so you can see that if something happens that, say, destroys the bottom of this food web, there are going to be repercussions all the way up. My favorite thing about this diagram is that it's a simplified food web. So I'm going to tell you a little story about what happens if you don't think about the system. If you don't think about what side effects are going to be, what the long-term implications are, you have to, if you're going to understand what repercussions can be, or what co-benefits can be, you have to think about the system. So this is an example of the World Health Organization not thinking about the system. So in 1950s Borneo, they were having a really big malaria problem. And so they identified that it was the mosquitoes, and they had this new chemical that was a miracle chemical to fight mosquitoes. So they started spraying it about willy-nilly. Now, as you can see, this is a place where there's a lot of water, so there's a big aquatic ecosystem, and biomagnification can happen. And it's a place where, you know, they don't have a lot of protection from the elements as well, so they're probably breathing it as well. Well, what they found was that not only did the DDT kill mosquitoes, but it killed the wasps that laid these disgusting looking eggs on these caterpillars. And these are the caterpillars that would eat the thatched roofs of the huts in Borneo. So they ended up with the caterpillars magnifying like crazy and eating all the thatched roofs. They thought, oh, well, we'll just put metal roofs on the huts. Well, then whenever it rained, nobody could sleep because it was so loud, and it rains a lot in Borneo. But that was not the worst. The worst was that, as you saw with the previous example with the wasp, when they sprayed DDT, it didn't just kill the mosquitoes, it killed and contaminated a lot of other insects. And there are a lot of geckos in Borneo that eat insects. So as I described before about DDT or other pesticides magnifying up the food chain, magnifying up the food web, this DDT was magnifying up the food web from the insects to the geckos to the cats that like to eat the geckos. You'd be amazed at how many photographs one can find on Google if you Google cats eating lizards. So the cats ate a lot of lizards. The whole point being about biomagnification is that the more of something from a lower trophic level that you eat, it just magnifies, and then it magnifies up. So they eat a lot of lizards, and it kills the cats. Well, when the cats all died, the rats started multiplying big time. They ended up with typhus and Sylvatic plague instead of malaria. So the Royal Air Force and the World Health or Operation Cat Drop, and they airlifted cats into Borneo to eat the rats and the mice. So I love this. Sort of definition of systems here by Garrett Hardin, and he says, side effects are consequences you didn't think of, the existence of which you will deny for as long as possible. So we did eventually ban DDT in the United States, but it is still used some places in the world. Not good. So William McDonough, who wrote Cradle to Cradle, which I'll mention later, says, we need to take the filters out of the pipes and put them where they belong, in the designer's heads. And so the way I see it, y'all are the designers for the chemical field. So I wanted to give you a little case study about green chemistry. There was a plant in Germany, and they had fabric trimmings from their chairs that they weren't allowed to put in the landfill because they were classified as hazardous waste, which they were hazardous. Their goal then, they decided, they shut down the plant, and their goal then was to go from their fabric as hazardous waste to make it safe enough to be mulch for the garden club, okay? They reevaluated the whole system. They were using 8,000 chemicals. They got it down to 38. So there, when you think about that in terms of purchasing, managing toxic substances, having to throw away hazardous waste, when you go from 8,000 chemicals that are toxic to 38 chemicals that are not, you've changed the expense of your process a whole lot, as well as the safety of your process, as well as protecting your workers and the people who live around your plant. They ended up with an entire line of fabrics that I don't even think they lost any colors in the dye lots. They had, you know, something that was great for their product, and the water coming out of the plant was actually cleaner than the water, drinking water, potable water that was going into the plant. And that was because the fabric even worked as a filter. And they ended up with, quote, fabric so safe you could eat it. So it's the same product. Amory Lovins used to say, people don't want coal and electricity. They want cold beer and hot showers. So how do you make what you need in a way that does it in a sustainable way? So we need to think then about what do we need and how would nature do it? So the Biomimicry Institute has looked at ways to do just that. And so the goal of biomimicry is to create products, processes, and policies, again, new ways of living that are well adapted to life on Earth over the long haul. And so the writer of Biomimicry points out, nature has already solved many of the problems we are grappling with. Or as Amory Lovins would put it, what worked survived, and what didn't was recalled by the maker. So there are some principles about how nature does things. And the first one is that nature sustains. So if you look up sustainability or sustain in the dictionary, it's got two things. One is it nourishes, nourishment, and the second is it continues. And nature really functions in these ways. It provides us with everything we need, and it does so in a way that is cyclic and can do it forever if we don't muck it up. Nature uses renewable natural energy. It's endless, it's free, and a spill is called a nice day. So we don't, down here at the police station, we just finished cleaning up a bunch of coal ash that was buried by the university decades ago as a result of, you know, waste from the power plant over here. So yeah, the renewable energy doesn't have coal's problems, and fracked gas actually has a higher greenhouse gas footprint than coal does. So we really need to get to renewables. In nature, diversity is necessary, beautiful, and adds resilience. And so when you think back to that cod food web, you saw that there wasn't a one-to-one, you know, it wasn't a simple chain. It was a very, very complex web. That's because if something comes in and it kills off one species, there is a redundancy in the system with some other species who can fill that niche until that species can come back. So the strength that is in nature is in a large part because that diversity creates resilience. Nature uses life-friendly chemistry. Okay, so on your left, you have the bulletproof vest made out of Kevlar, right? To make Kevlar, you have to take toxic chemicals and boil them at very, 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 very high temperatures for long periods of time at great expense in terms of energy and a lot of toxic substances. Meanwhile, a spider's silk is stronger than a thread of Kevlar, and it makes it at ambient temperature out of bugs. Nature evolves and adapts to conditions. And so that's how it is that, you know, we have worms living in sulfur laden ocean water at high temperatures at the bottom of the ocean. And we have birds that live on the wilds of Alaska, you know. So here is an example of termites that have made a nest. They make these towers in their nest, and they even though it's a very, very hot environment there in Zimbabwe, these termite mounds are self-cooling. And so there's this office building in Zimbabwe that was built to mimic the function of this termite mound and to be able to be self-cooling in a hot environment. So one of the bad things about air conditioning is that we really lost the endemic, the historic architecture that people built from place to place to meet the needs of their place. So if you look at the tents that they'd use in the deserts of Africa or the Middle East, they were built with a fabric with lots of holes in them, so there would be a lot of air that would go in and out. But when it started raining, the fabric would swell and close up so that the rain wouldn't get in. And so human architecture worked a lot like, you know, animal and insect architecture until we invented a way to get away from needing to be cognizant of our place and the conditions of our place. And one of the most important is that nature recycles everything. So everything in nature is in a cyclic creation and destruction circle. And so we've seen that with the water. You know, everything where waste equals food is a big lesson for green chemistry. So, you know, the tree falls in the woods, the mushrooms come in first, because the function of mushrooms is to break down hydrogen-carbon bonds. The bugs couldn't do it by itself. The moss couldn't do it by itself. The mushrooms, the fungi have to come in first, break those carbon-hydrogen bonds, and then everything else breaks all of it down, turns it back into soil, and it becomes another tree or whatever. So those are the sort of the settings for green chemistry. Because I worked at EPA for a long time, I'm opening here with the EPA green chemistry page. There's a lot of cool stuff on this page. One of the most fun of which is that there are Green Chemistry Challenge Awards. So y'all can look into those and see. It's always fun to do these challenges where we can let people think about, you know, what's possible, rather than saying, well, just put a filter on it and we'll worry about it, you know, later, the waste later. So we've actually learned a lot from putting out these challenges and letting younger people who are still often very in school. We've had some that, you know, not necessarily ours, but some of these challenges have been high school kids even. So, you know, it's a matter of thinking a new way. So I mentioned William McDonough earlier. He wrote he co-wrote with Michael Braungart. So William McDonough is an architect and Michael Braungart is a chemist. And they wrote this book, Cradle to Cradle, Remaking the Way We Make Things. And so basically they set forth this design framework that was characterized by these three principles that they picked from nature, that they saw in nature. That everything is a resource for something else. And so again, they're looking at this food equals waste paradigm, but also breaking it down to two kinds of metabolisms: biological nutrients, where they can be grown and then become part of the, the kind of like that fabric, or kind of like food and trees and all that kind of stuff. So if you make a fabric that, that you then uses mulch that will break down, if you can make paper that will then be biodegraded, those kinds of things. But there are other things that we use that we cannot make out of, we can't make a computer out of wood. We can't make the hardware of the functioning part of a computer out of wood. And for that, we need technical nutrients, but we need to be able to reuse those technical nutrients. There are so many old cell phones in landfills, and those are valuable things like, the rare earth elements and a lot of crappy plastic and all this stuff. And if those things can be reused, we don't have to get more we don't have to get more oil or whatever to make them. We can just reuse the old technical nutrients. But in order to do that, you have to design it to be recycled. There we go. Okay. So once again, you have to go in with the filter in the designer's minds. How am I going to create this product such that it can be recycled and reused infinitely in an infinite loop? The second principle, of course, is to use clean and renewable energy. And the third is to celebrate diversity. So here's a couple of places that you can look to sort of delve into this more. Michael Braungart and William McDonough came up with this Cradle to Cradle Products Innovation Institute, which is more of a development place. And then they've got Green Blue, which is a sort of a consultancy place. Both of those work on developing cradle to cradle type products and assistance. I loved finding this Beyond Benign Green Chemistry Education site. That just sounded really cool. And it reminded me of a story I heard where a chemistry teacher in a high school, I think he started out running out of money for materials, for new chemicals for the lab. And he decided to make an exercise out of sort of taking the products and transforming them back into the original materials. And they use that as an exercise. So very interesting, because what he did was, again, he thought about it in a different way to be able to do a cyclic approach. And then there's the Biomimicry Institute, which tends to be not as much chemistry as more of a physical kind of thing, but it's still very cool. And I think that a lot of chemistry could be biomimicry. I would love for somebody to make bulletproof vests out of spider silk, for example. This is a really cool little pocket guide from the American Chemical Society Green Chemistry Institute. And they have the nice definition of green chemistry. And I thought this was fun, where they talk about green chemistry is using catalysis and biocatalysis to improve efficiency and reaction. So yay, y'all. And I wanted to end with this one, because this is a picture that I pulled out to tell a story to some school kids about biomimicry. And there is a new bullet train in, I think it was Japan. And they ran up against a problem, which was when the bullet train came out of the tunnel, it created a sonic boom, which really annoyed the people who lived nearby. And so they set back, and the engineers looked at the bullet train, and they looked at it from a biomimetic perspective. And they thought about the kingfisher. So this is a kingfisher. And they thought, well, when a kingfisher, they thought the thing about biomimicry is like, what animal is trying to approach the same kind of issue as we are? So we're looking at a fluid dynamics kind of a thing, with the train coming into a different, coming out of an air pocket into a different atmospheric environment, right? Fluid dynamics. And so it's very like when the kingfisher dives into the water to catch a fish, he does not make a splash. So they used the knowledge from the kingfisher to remake the bullet train, which solved the sonic boom problem, cut down on the drag, so it increased the energy efficiency, and it made it faster. So they ended up solving one problem and coming up with 3 different co-benefits for that, with that solution. And that's really the keys to a lot of this, is not only preventing or solving a problem, but where can you get additional benefits, because this is a system. And there will likely be additional benefits like savings, resource savings, safety benefits, those kinds of things. So this is a quote I really like: with our every deliberation, we must consider the impacts of our decisions on the next 7 generations. So the Iroquois had that as part of their approach to everything. And if we had that approach to everything, we would be in better shape than we are now. But if you don't plant if you didn't plant an apple tree 20 years ago, the best time to plant it, second best time to plant it, is now. So since this is about careers, I felt that this was more important to talk to you about than to tell you about mine, because mine doesn't have very much to do with chemistry at all. But I wanted to leave you with this sort of one last thought, which is that the real question is not what careers are there in sustainable chemistry. The real question is, how do you guys change all the chemical careers that are out there so that they are about sustainable chemistry? And with that, I'd like to open it up for questions and discussion.